a very important. This is a very important issue, and we will listen for speakers, and we will start with Ahmed. He is working at the Gas Exporting Countries Forum. So I leave you the floor for 20 minutes, Ahmed.
Yeah, thank you very much. Thank you very much. I don't know if the screen is apparent on the. It's okay, or I need to share again.
You have to share it again, I guess.
Okay. It's okay now. Yeah. Thank you very much for giving me this opportunity to talk on the GCF, the Gas Exporting Countries Forum view, on the possibilities to reduce the emissions from the power generation sector. Just my name is Sid Ahmed Hamdani, so I'm energy policy and environment analyst at the GCF Secretariat. So the GCF is a gathering of major gas producing countries, producing and exporting countries. They export more than 50% of the global gas. In this presentation, I will be talking first on the here. Okay. Yeah. I will be talking first on the power-related CO2 emissions, the present situation of the power-related CO2 emissions. After that, I will present the methodology and the key assumptions for the methodology used, which is the scenario analysis, to investigate the decarbonization long-term pathways of power systems. And after that, I will present the results from our modeling. So at the beginning, I would like to show the recent developments of the CO2 emissions in the in different sectors, including the power generation sector. And you can see here that the power generation is responsible for the largest emissions. We see that after 2017, there is a stagnation of the emissions and the drop in 2020 because of the COVID-19 outbreak. But even with that, power generation remained the largest contributor in the emissions. In 2020, power generation was responsible of 36% of the global energy-related emissions. So power generation has large possibilities to decarbonize, large existing options and technologies, well-proven technologies to decarbonize. And in this exercise, we strive to show what are the alternative pathways that we can consider for the power generation sector to reduce the emissions. So we investigate the decarbonization pathways through the scenario analysis. So we developed what we call the CMSP. CMSP is the carbon mitigation scenario for power. We use a future forward-looking approach. It means that we assess the feasible future based on the present forces that drive the low carbon transition. This differs from the backcasting scenarios or backward-looking scenarios that fix the targets and see what are the pathways that allow us to meet the targets. So what are the main present forces that we consider? The policy pledges and orientations, the concrete actions and instruments for the implementation of these policies, the technology trends, and also the challenges faced by different countries to deploy carbon mitigation options. We consider assumptions on different decarbonization drivers. We have 5 main decarbonization drivers. First, the deployment of renewables and storage systems, the deployment of other carbon-free technologies, I mean nuclear and hydrogen for power, the electrification of energy systems. Also, there is the interfossil fuel substitutions, coal to gas switching, oil to gas switching, and also the power emission abatement through the deployment of the CCS. So here in this slide, I want to show the main assumptions that we consider in both the reference case we developed for our forecast and the carbon mitigation scenario for power, the CMSP. Let's start with renewables. We have already considered in the reference case strong deployment of renewables. However, the ambitious targets set by different countries are missed in many countries because of several challenges. First, the cost of technologies, the cost of integrating intermittent renewables, reinforcing the power networks, the availability of spaces, and also the supply chain barriers, like we saw it in the US and also even in India with the taxation or the increasing cost of solar panels. I can also refer to another driver, which is the electrification of energy systems. In our reference case, we consider the share of electricity in final consumption by 2050 for the residential sector at around 33%, one-third. For the industry at around 43%. There is also the share of EVs in the new sales by 2050 is estimated at one-third in the reference case. In the CMSP, we increase significantly these shares. The residential sector will increase, the electricity in the residential sector will increase to 40%, and it is driven by the deployment of electrical equipment, especially the electrical heat pumps. For the industries, the share of electricity in the final energy consumption by 2050 will increase to 50%. We see or we consider larger electrification, especially of the low heat grade processes in the manufacturing industry. There's also or there is increasing electrification in the energy intensive industries. For example, for the steel industries, we suppose a larger development of the EAF processes, I mean electrification arc furnaces. Also, for the coal to gas or oil to gas substitution, we consider in the CMS larger penetration of CCGT and also of open cycle gas turbines, especially in the developing countries and emerging countries, in order to meet the increasing baseload power needs and also in order to meet the increasing requirement for flexibility because of the penetration of renewables in these regions. We consider also in the CMSP more aggressive retirement of coal and oil because of the phase out mandates and also because of the environmental restriction on coal. For the CCS deployment, in the reference case, the CCS was very small deployment, mainly pilot projects in different countries. But in the CMSP, in the advanced scenario, we consider a non-negligible deployment of the CCS for gas and coal power plants. Here in this slide, I show the main policies that we consider and that we assess in order to make our assumptions in the CMSP. What we can say here, we see that the EU here, we see that the EU is at the forefront of the climate policy commitments. We see very strong targets and policy engagement through the net zero emission pledges, especially in the framework of the Green Deal agenda. We see upward revision of renewables targets also. We see there is announcement of reforming the carbon pricing market, especially the phase 4 EU ETS reform, which plan to strengthen the emission allowances caps. All this will have an impact on the carbon prices. In the US, the new Biden administration has strong engagement, pledging especially free carbon power system by 2035. So we assess this policy development. Other policies we consider also are more state-level related policies, such as renewable portfolio standards or also carbon pricing, which is more based on regional initiatives in the US, in California, also in the eastern states of the US. In China and India, there is strong engagement in renewable development with strengthened renewables targets, but also the two countries are considering policy support to gas penetration. India, for instance, the Prime Minister has announced 25% of gas penetration by 2030, which is a very aggressive target. So when we take all these policies, so we factor in these policies in our model, in the global gas model, especially the power module of the global gas model, in order to have this CMSP scenario. Here in this slide, I would like to talk on the levelized cost for various power generation technology that we consider in OECD Europe. Why Europe? Because, as I said, Europe, the climate policy is very important, and I want to highlight here the cost of decarbonizing the power generation sector in Europe. What we see here, we see that wind onshore is the most competitive option for generating power in the EU. But also natural gas is well positioned in the EU. Why? Because we have experienced recently a drop of the gas prices, but also an increase on the carbon prices that gives some opportunity to natural gas and penalize coal power plants. We see here that coal power plants cost is higher than the gas power plants cost. Solar, we see solar is in the middle of the ranking. However, we see a huge range between the minimum cost and the maximum cost in the solar. Why? Because the difference in the capacity factors between countries which are exposed to solar, like Spain, Italy, and the ones which are less exposed in the northern Europe. The most expensive option is the fuel cells, hydrogen fuel cells, and this is because of the investment cost, of course, and also because of the cost of hydrogen supply. In Europe, hydrogen is estimated to be around $2 per kilogram in the EU. And here we base this mainly on gas, but also we consider a mix between gas and renewables. What are the main results that we obtain when we factor in all these assumptions? First of all, let's talk on the electricity demand. Here in the CMSP, what we see larger electricity demand compared to the reference case. By 2050, 5% increase of demand. And this increase, when we take the average electricity demand growth, we see that it increases in the CMSP in almost all the regions, even in the more mature electricity market, such as the EU and also North America. When we consider the electricity demand growth at sectoral level, what we can see here, we can see that the transportation sector is the sector that will experience the highest share the highest momentum of its demand growth because of the penetration of EVs. Nevertheless, for the industrial sector and the residential, the growth of its demand in the CMS is mitigated by the improvement of efficiency, which is also factored in this scenario. In order to meet the electricity demand growth, here we show the capacity, the installed capacity deployment. From 2019 to 2050, we need a huge capacity addition, almost doubling the current capacity by 2050 in the reference case. And this capacity will also increase in the CMSP by 25%. So what we can show here is that electricity demand will increase by 5% compared to the reference case, but the capacity will increase by 25%. Why? Because of the low utilization rates of renewables. Renewables will be the major capacities that will be added to the global systems, and renewables have low utilization rates, and because of that, so we need more capacity to meet the electricity demand. Renewables, if we take intermittent renewables, it will represent 55% by 2050. Now, if we see the development at regional level, here in the left side chart, we show the incremental coal and gas capacities by region between 2019 and 2050. What we see here, we see that there is a significant replacement of gas capacities with coal capacities, especially in the CMSP, in non-OECD Asia, especially in China. China has announced gradual phasing out of coal, limitation of coal, and this coal capacity, there is room of development of gas capacity to replace this coal capacity. In North America, also there is significant replacement of gas capacities, of coal capacity by gas capacities, and because of the availability of large gas resources, and also the gas allows to reduce emissions. However, for North America, if we take the US, a significant share of these gas capacities will be equipped with CCS because of the pledge, the American pledge to meet net zero emission, net zero power-related emission by 2035. So CCS will play a significant role in the US. In the right side chart, here I show the incremental wind and solar capacities by region. And we can see that the solar will be the major additional capacity between 2019 and 2050. in the reference case and even in the CMS, wind will increase, especially in North Asia, but also in Europe. The additional wind capacity will be significant in Europe. Now, if we talk on the electricity generated by different sources, what we see here, we see that intermittent renewables in green will largely take the lead in the power generation, supported by capacity development, but also by improved integration of renewables. We have the difference between the reference case and the CMSP is that there is larger deployment of flexibility options, demand side management, batteries, even hydro pumps, and this will improve the integration of renewables, and this will lead to larger generation of electricity generation from renewables. However, we see increase of natural gas based generation that replace coal, especially after 2035, which is due to the decline of coal, especially in North Asia and China in particular. There is one
5 minutes left. 5 minutes. Okay.
Yeah. So here, the one key insight from this slide is that the average utilization rate of power capacity, we see an increase of the coal-based average rate. Average utilization rate of coal-based capacities. Why? Because of the decline and decommission of coal. So what are kept in the systems only the efficient power plants, coal power plants that work mostly in baseload power generation. There is also improvement in the utilization rate of renewables because of the flexibilities, but gas-fired power plants will decrease their utilization rates significantly. Why? Because they play more a role of backup and balancing of renewables intermittency. Here, I would like to talk on the role of hydrogen in the power sector. So hydrogen has several advantages in the power sector. Decarbonize the power sector. Also, it can be used as a storage option through power to gas conversion and storage, managing the excess of electricity production, enable the hydrogen for power, enable also coupling with different sectors through power to X. X means liquids or even gas that can be used in different sectors. Hydrogen also for power can benefit from the repurposing of existing gas infrastructure. However, there are several disadvantages of hydrogen in the power sector. First, the lack of competitiveness in the power generation, and I showed the levelized cost for hydrogen fuel cells in Europe, which is very, very high. The cost of hydrogen supply chain, the lower volumetric density of hydrogen. For instance, for storing hydrogen for the same amount of energy, we need 3 to 4 times more space to store hydrogen than natural gas. The low efficiency of reconversion of hydrogen to electricity. All these are limits to hydrogen, and this will lead to a low contribution of hydrogen in the total electricity generation, around 1.3%. For the deployment of CCS, there is significant potential, especially in North America, in the US, especially because of the availability of storage capacities with the depleting fields there. So the US, we expect that the CCS will be strongly deployed to reduce the emissions from the gas-fired capacities. There is also significant deployment in North Asia, China in particular, to use these coal-fired capacities. The potential of CCS related CO2 emission saving is around 2 gigatons CO2, we estimate by 2050. Now, if we consider the impacts of all these developments on the power emissions, what are the potential? What is the potential to reduce emissions? If we consider the CCS, if we include the CCS, the potential compared to the reference case is 50%. 50%. If we exclude the CCS, it's around 1/3. This is because of the decline of coal power plants in the power generation systems. However, one key insight is that the increase of gas will increase the emission from gas power plants in the reference case. I mean, in the CMS when we exclude the CCS, but when we include the CCS, we can reduce significantly the emission from the gas-fired power plants. At regional level, the potential is specifically in North Asia with the decline of coal there. North America also with the replacement of coal and also gas play a role in reducing emissions. Europe has less potential because in the reference case, the emission is already, I mean, the carbon intensity of power system is already reduced, and we can reduce it more through the deployment of renewables. Renewables will be the key driver of reducing emissions and allows to replace the coal decline, but also gas fired power generation play a role in North Asia. We see here that gas will increase in North Asia. In the Middle East, it plays also a role in North America due to the large availability of gas in this region. As a conclusion, what we can say, what are the main takeaways from the development of the CNSP? First, emissions can be almost halved with a larger penetration of gas and renewables compared to the reference case. This mitigation is mainly based on greater dissemination of existing technologies. The existing technology. If you want to reduce further emissions, we need to develop new technologies and innovate. And also we need to do more efforts in order to ensure more technology transfer to the developing countries. There is large disparities in the emissions mitigation between different regions, depending on the level of climate policy ambitions, the potential of coal to gas switching, and also of scaling up renewables. Intermittent renewables will largely take the lead in global power generation, supported by capacity development, but also, and it's important, by the improved integration of renewables in the networks due to improved flexibilities deployed for power systems. The global required installed capacities will substantially increase, pushed by lower capacity factors for renewables and larger electrification. The gas-fired power plants are increasingly involved in backing up renewables intermittency with lower utilization rates and revenues. This put a huge challenge for the gas capacity owners. They will miss money and revenues, and this puts also some policy instruments like capacity mechanism, or also pushing for better gas renewables integration in order to keep these gas power plants in the system and to keep them profitable. The deployment of CCS reinforces the mitigation role of natural gas. We estimate that 15% of the total thermal capacities can be equipped with CCS. Almost 2/3 of these capacities are gas-fired capacities. So thank you very, very much. So this is, and I'll be ready for questions.
Thank you so much, Ahmed. I was very impressed with this broad panorama and with very interesting conclusions. So a very synthetical overview of what could happen, or what we could expect, or what we could hope. And again, this work provides us with the conclusions that CCS and Asia are the two main, not obstacles, but issues regarding the way we will achieve the 2050 goal. What will happen in Asia, and whether CCS at last will be able to be deployed. So thank you very much. We have to go now to the second talk with Giacomo Benini from Stanford University. Giacomo, you started to share your screen. And Ahmed, we will have a Q&A discussion after, okay? So thank you very much, Ahmed.
Yeah.
So welcome to you, Giacomo.
Can you hear me?
Yes, I can hear you. I can see you. I can see your slides. So thank you very much, Giacomo, to be with us on this session. And I leave you the floor. Okay.
So just before starting, let me just say that here is almost 1 a.m. I'm in San Francisco. So I am literally falling asleep. So this might not be the best presentation you've ever seen. And especially, you know, to Jasmin and Emilie.
No, it will be the best presentation we've ever seen, Giacomo. So be comfortable.
Maybe I will fall asleep in the next 10 to 15 minutes. So sorry if I will not be super attentive to your presentations. So, okay. we are talking about methane emissions. There are different measures of it, but we are talking about roughly something a little bit above 15% of the total GHG emissions that we observe in the atmosphere. Out of this chunk of emissions, that is the core of this research project, the ones that are due to the energy sector are the relative majority. And all in all, they represent something in the neighborhood of 6.5% of total GHG emissions. So these are the emissions that we are going to discuss today. We are going to discuss a little bit the origin and if there are ways to reduce them. So how do they originate? Well, essentially, you emit methane every time you have to do with hydrocarbons. In particular, when you're mining for coal, once you start mining, the mine releases coal that is trapped beneath itself, and but also when you are interested in the security of the people working in the mine, you have to constantly ventilate the air, and even if the methane content is less than 1% of the air, this represents a great release of methane in the atmosphere. This is not going to be the focus of my presentation, but I'm writing something on methane emissions from the coal sector. So if someone has questions, I would be happy to answer. But today we're going to focus on methane emissions that are that come from the oil and gas sector. And why do we have methane emissions from the oil and gas sector? Well, because we have what economists call an associated commodities channel. Namely, you have that oil wells produce associated gas, and in the same way, gas wells produce associated liquid hydrocarbons. And we're not going to focus on the second case, which is a little bit less interesting from our perspective, but we're going to focus on the first one. So namely, what we are going to see during the rest of the presentation is that the gas that you co-extract together with the oil is the crucial source of methane emissions from the energy sector. Okay. Think about it. Think it this way. You have an oil well. You're there to find oil. The well starts boring the earth. It goes down. And then when it reaches the deposit, the engineers decide the degree of openness of the well. Once the engineers have decided that, what you have decided is the volume of oil that is going to come out from the well. The quantity of gas that comes out you don't have much control on it. Okay, so once you decide how much oil to get out of it, the quantity of gas that is co-extracted is pretty much a state variable and not a control variable. Okay, so what do you do with these two things that come out simultaneously from the same well? Well, you're there for the oil, so you're definitely going to sell the oil, but what do you do with the gas? Well, here, of course, we have a direct answer being economist. If the marginal cost of productions are smaller than the market price, well, you sell it, because every other standardized cubic feet of gas that you sell, you are increasing the revenues of the field and those the profits. But what happens when the marginal cost of production are bigger than the market price? And this happens in a lot of cases, especially if you are managing an isolated field that is not well connected to the pipeline infrastructure. Maybe you are offshore. Maybe you are in a region where there is a lot of traffic in the pipeline. You need to get rid of it. And how do you get rid of it? There are essentially two options. The first one is to just release the gas in the atmosphere. This operation is called venting. And the second action that you can do is just you combust the gas at the production site. And this procedure is called flaring. Now, the combination of these two activities create a lot of externalities. The first one, of course, is an environmental externalities, in the sense that the combination of flaring and venting of natural gas contributes to roughly 6% of global GHG emissions. So if you remember the initial pie chart, it's almost the entirety of the methane emissions we are analyzing. It's so big that for some small open economies that focus on oil and gas exports, they could achieve the Paris goal agreement simply by reducing flaring and venting to zero. So for example, you know, for Iraq, Algeria, Yemen, they just had to reduce flaring and venting to zero and they would meet their Paris agreement targets. Also, there is an economic externalities because we are throwing in the bin 8% of the global gas production, and it's gas that we could use for other scopes. And finally, there is an environmental effect because people living close to these areas where you observe a lot of flaring and venting observe a higher percentage of respiratory diseases. And with the Stanford Med School, we're just starting a project on this. So in 2015, the World Bank said, enough, basta, ça suffit, genug. With this thing, we don't want to do it anymore. And a bunch of countries signed an agreement, which was called Zero Routine Flaring by 2030 initiative. And the idea is that, let's suppose that field I at time t co-extract a total quantity of gas called total gas. And now part of the gas is sold, is this quantity here gas that's sold, part of the gas is flared, so you combust it on the spot, and part of the gas is vented. And the aim of the World Bank is to get rid of flaring and get rid of venting and make sure that all the gas that is co-extracted together with oil gets sold on the market. Now, how can we reduce flaring? Well, flaring is observable from satellites. We have quite precise measures. We just have to match the color of the flame and its size. And so it's not unreasonable to say that the information available to the regulator is very similar to the true information. You see here, this flare with the tilde is the quantity of flaring observed by the regulator, and this flare here is the true quantity of flaring. Therefore, it is possible to think about some form of regulation in quantities, okay, of whatever kind you may want. With venting, things are a little bit more complicated. There is a lot of asymmetric information. The quantity of venting observed by the regulator is very, very different from the true quantity of venting, and I will tell you more about this in a few seconds. Therefore, the regulation in quantity becomes more problematic. But why? Where does the asymmetric information problem originate for? Well, first and foremost, you have a measurement error in the sense that we have bottom-up measures that are operated with laser pistols and just with cars driving around production sites. But you also have top-down that are operated with airplanes and satellites, and they usually report very, very different numbers. And especially it seems that the bottom-up consistently underestimate the quantity of natural gas that is vented. But it's not only that. The venting has two origins. Part of it is intentional. You see here, this is an oil tank. And at the bottom of the oil tank, you have the oil. And on the top of it, you have all the part of gas that wasn't separated by the heater treater. So in order to recover that gas, it's quite expensive. You need to repressurize it and sell it. Instead, you can say to a guy, just go on the top, open the oil tank, let the gas go in the atmosphere, and let's just sell the oil, okay? And this is intentional. But it's not always the case. Sometimes you have unintentional venting. Maybe the pressure in your gas equipment is too high. You fear for the safety of the workers in the workplace, and you just release some gas in the atmosphere. So the quantity of venting observed by the regulator is very different from the true one, because what the regulator observes is a sum between the volume of gas that has been vented intentionally plus the sum of gas that has been vented unintentionally, adjusted by a possibly large measurement error. And in particular, in this research that I made, we assume that the error term was Pareto distributed, meaning that the regulator has a very, very high probability of committing a very small measurement error and a very, very small probability of committing a very large measurement error, okay? And so if you think about it, okay, so you are in a situation where the management of the oil and gas operation has to solve a gas management problem, where you're trying to minimize the losses that you would have if you would sell the gas. Remember that in this particular case, the marginal costs are bigger than the price. So this quantity here measures your losses, and you want to minimize the losses. Then you want to, you have to take into account the cost of flaring. And then you have to take into account the fact that if you flare a quantity that is bigger than the one that the regulator wants, in this particular case, I said 0, then you're going to pay a flaring fee. And here, if you do intentional venting more than the quantity than the regulator allows, you're going to pay a venting fee. But contrary to the flaring fee, the venting fee that you're going to pay, you pay it stochastically. You have a probability of paying it just if the regulator catches you. And this probability is increasing in the quantity of venting that you do. The more you transgress the rule, the more likely it is that the regulator is capable of making you paying a fee, but is not certain. And you try to solve this minimization problem, having the total quantity of gas being equal to the quantity of gas that you sell to the one, plus the one that you flare, plus the one that you vent. It's a little bit hard to discuss this problem because the naive first order conditions do not work. You have to discuss the entire Kuhn-Tucker problem, which is always a pain. But you can see that in equilibrium, the co-presence of flaring and venting regulation makes the total quantity of flaring that you would do goes down. Okay, so you flare less gas that otherwise you would in absence of regulation. And what do? Well, a part of gas that otherwise you would have flared, you now sell. And this is good. This is what the regulator wants. Okay, but a part of gas that otherwise you would have flared, you now vent. So there are two substitutions effect. And this first substitution effect is good, is what the regulator wants. But the second substitution effect is unintended and is the result of positive marginal flaring cost on one side, and on the other, imperfect monitoring capacity of the regulator of the intentional venting. This could be quite bad from a climate change point of view, because as you all know, methane has a higher global warming potential than CO2. And so depending which time frame you want to have, this is, but even if you take a reasonably long horizon of 100 years, methane still is more than 25% more potent than CO2 as a GHG gas. Okay, so even if this, even if the yeah,
Giacomo.
thanks. Even if the substitution effect is very small, then you're going to have some environmental problem. So I wasn't sure that my result made any sense because it just made the math. So I started calling around people in the oil and gas industry, and I got some answer, especially from North America, and I talked with quite some people in the business who I'm not going to name, but they said, yes, we have now, we flare less and we do less because regulation is very biting, but now we have started venting much more. And, you know, Canadians are genetically incapable of lying, so I generally speaking trust the answers I got. So I said, okay, I now have this this intuition. How can we solve it? I constructed an economic model where there are many agents, and in particular, there are consumers, oil and gas firms, refineries, natural gas processing facility, power plants, and there is the state. And then I tried to solve the problem from the point of view of a social planner. And then I compared it to the solution of a decentralized economy where there are all the problems that we just discussed about imperfect monitoring. And I I showed that the two equilibria are different because the social planner finds an optimal quantity of flaring equal to 0, an optimal quantity of venting equal to 0, while the decentralized economy does not. So I proposed an optimal taxation strategy to solve the problem. It's very traditional in the sense that you just readjust in a non-Pigouvian way, but is not super complicated. The problem is that the solution I found to make sure that the social planner solution equals the one of the decentralized economy requires to tax marginal carbon intensity from different sources, and this poses a series of legal problems that seems to be incredibly complicated to solve. So I thought about a second solution, which is to get rid of all flaring and venting regulation and then increase marginally taxation on oil and rebate part of the extra revenues that you make from an increased oil taxation to gas production, so that all in all, the oil and gas industry taxation stays constant. But with this rebate system, you make sure that the incentives of the regulator and of the regulated go in the same direction. Therefore, the asymmetry of information between the regulator and the regulated does not matter anymore. And then I added a second taxation in the power sector to exploit the interfuel elasticity of substitution that we also saw in the previous presentation between coal and gas. And so at the end, what happens is that this is the equilibrium in the gas market, and with the type of taxation that I propose, at the beginning, you increase the supply of natural gas because you get a lot of gas that now is flared and vented, goes into the market because it's now profitable to produce it. But at the same time, by exploiting the interfuel elasticity of substitution within the power sector, you substitute coal with natural gas, and therefore the price of gas returns in equilibrium, and you don't artificially generate a technological advantage for natural gas vis-a-vis other technologies. Thanks.
Thank you so much, Giacomo.
Yeah, I also did a lot of things with the data. There is a lot of data, but not time to talk about it. Sorry. Yeah.
Thank you so much, Giacomo, because it is so important that economists does not always go to work on the same topic. And your topic is both very important and interesting from an economic perspective. It is important for society, but it is also interesting from an economic point of view. So congratulations to have chosen this subject. Because I was very impressed with your 6% of global emissions from venting and flaring. So we have to do some things, and I will have a question at the end regarding the imperfection of the regulator. Okay, so very good. After a first one, the first talk very interesting. The second talk very interesting. So what about the third one? I'm sure that it will be equally very interesting to get. So I give the floor to Jasmin Cooper from Imperial College London, and it will be on methane. So the floor is yours, Jasmin.
Thank you. Can everyone hear me? Can you see my slides?
Yes.
Okay, great. Thanks. Thank you so much. Yeah, so actually, I think my presentation follows on quite nicely from Giacomo. So,
maybe you could put full screen.
Oh, I'm not too sure how to get rid of this. Oh, there we go.
Okay.
That's better. Yeah, so I think my presentation follows on quite nicely from Giacomo. I'm Jasmin. I'm a research associate at Imperial College London in the Sustainable Gas Institute, and I'm going to be showing some of the work I've been doing on estimating methanes for the world's largest gas supply chains, as well as assessing the underlying emissions data that's reported. I'm a chemical engineer by background, so this presentation is going to be slightly different to the other presentations in this session. So just warning. So in this presentation, I'm going to start by going over why methane is important. I won't dwell on it too much. Giacomo already covered most of it. I'll then go over the methods we use to estimate emissions and how we conducted our uncertainty assessment. I'll then go through some of our main results and then finish with our main conclusions drawn. Before I get onto that, I want to start by very quickly thanking the institutions that fund the SGI and pay my salary. So thank you very much. So starting off with the presentation. So as Giacomo said, methane is a highly potent greenhouse gas. In comparison with carbon dioxide, it has a much higher global warming potential, which means it's much better at trapping heat. So over shorter timeframes, this heat trapping potential is much greater. But on 100-year time frame, the 1 kilogram of methane can trap as much heat as 25 to 36 kilograms of carbon dioxide, and methane is the second most important greenhouse gas, and it's estimated that since pre-industrial times, around 20% of anthropogenic global warming is caused by methane alone. So methane has become more prevalent in mainstream media, mostly related to the threat it poses to meeting emissions targets, specifically Paris Agreement targets. In the quantification of methane, there's a lot of uncertainty around how much is being emitted from the various sources, especially in oil and gas. And that's where my research kind of fits in. So move on to what I've been doing. So we've been estimating emissions for the world's largest gas supply chain. So a supply chain, for anyone not familiar with the term, it's simply the process of producing gas and getting it to the end user. In the supply chain, we typically exclude the end use. So we consider all the stages up to distribution to the end user. The gas supply chain can be split up into 3 sections. The upstream, which is all of the stages from pre-production through to processing of natural gas. The midstream, which is the transport of the gas from the producer to the market where the gas will be used. So this can be in gas pipelines, so pipeline gas, or as liquefied natural gas, which involves liquefaction, shipping in cryogenic ships, and regasification. The final section of the supply chain is known as the downstream, and this is the transport of gas to the end user. So it consists of transport in high pressure transmission gas pipelines, any gas storage, and distribution of gas in the low pressure gas network to the end user. So to estimate emissions, we've done this for the largest gas supply chains, which consists of the 17 largest gas producing countries and consuming countries in 2017. And these 17 countries account for between 2/3 and 3/4 of all gas consumed, produced, and traded in 2017. These countries are listed on the slide. And in addition to these 17, we also included all the countries that imported or exported gas to and from these countries. So in total, we considered 80 countries and 252 gas supply chains, with supply chains being all the supply chains from domestic production, domestic consumption, pipeline imports and exports, and LNG imports and exports. To estimate your emissions, there are 2 key pieces of data that you need. Firstly, the emission factors, and also the activity data. So emission factors we derived from methane emissions reported in national greenhouse gas inventories. In these inventories, methane emissions from all the various sources within a country are reported. They're typically, for oil and gas, they're typically reported in units of kilograms per, either per 1,000 cubic meters of gas produced or consumed, or per million cubic meters of gas. These emissions are all our emissions from fugitives, venting, and flaring. Giacomo talked about venting and flaring. Fugitives are the emissions that are essentially fugitives are leaks. So they're the emissions that are unintentional, but they're different from leaking. They're different from venting in that they're accidental emissions. So emissions that are non-intentional. So from the emissions data reported in these inventories, we converted these into an emission factor, which is a percentage of methane lost in the atmosphere per unit of gas produced or consumed. The activity data is the gas throughput in your supply chain. So it can be the volume of gas produced, the volume traded, or the volume that is consumed. Simply multiplying your emission factor by your activity data will give you your methane emissions being emitted. We also assess the underlying emissions data. And by emissions data, I mean the emissions data reported in the national inventories. The countries that estimate their emissions, they can use one of three methods to quantify methane, tiers 1, 2, and 3. Tiers 2 and 3 are methods that are based on primary data, so based on actual measurements of methane from different facilities within that country, whereas tier 1 is based on de facto IPCC emission factors. And these are quite generic, as there are two sets of emission factors that can be used, those for Annex 1 countries and those for non-Annex 1 countries. Because the tier 1 emission factors are quite generic, we wanted to see the impact this had on our overall emissions estimates. So we conducted some bootstrapping resampling to resample our original data set and resampling it, omitting the tier 1 data, just to see how it impacted our overall emissions estimate. We also conducted a risk assessment to identify whether or not there are any countries that are at risk of high emissions, specifically at risk of not accounting for high emissions. For this, we developed a risk assessment where risk is the product of likelihood and consequence. Likelihood we define as the likelihood of inaccurately reporting your emissions, and this is based on the method used by the country in accounting for their emissions. And we assume that the tier 1 method has a very high likelihood of inaccurately reporting emissions, and tier 3 a low likelihood of inaccurate emissions. The consequence is the emissions intensity estimated, and this is based on our emissions estimate rather than the emissions reported in the inventories. We define the emissions to be high or low relative to a benchmark. We set this benchmark as the Oil and Gas Climate Initiative's methane intensity target of 0.2%. So any emissions less than that will have a minor consequence of high emissions, and anything above this 0.2% will be a moderate to extreme consequence of high emissions. So moving on to the results. Starting with the amount of methane emitted by the supply chains. Across our 252 supply chains, we estimated that around 26.4 megatons of methane was emitted by these supply chains. And to put that into context, if you convert the 26.4 megatons of methane into carbon dioxide equivalents, it's around equivalent to all of Germany's greenhouse gas emissions in 2017. So it's a lot of greenhouse gases. When we compared the different supply chains, there was a huge variation between them, ranging from less than 0.1 kilotons to as high as nearly 5,000 kilotons of methane. The majority of supply chains had lower emissions, and on average, 124 kilotons of methane was emitted per supply chain. But there are supply chains where there is a significant, outliers, specifically US domestic production and Russian domestic gas consumption are the two highest emitting supply chains. I'll go into more detail on the next slide on why this is the case for these two supply chains. Before I go on to the next slide, very quickly, for countries that are heavily reliant on gas imports, the country of origin for the gas will have an important impact on total emissions for those supply chains. If we compare Italian pipeline imports with German pipeline imports, we can see that the Italian imports have much higher emissions, and that is despite the fact that Germany is the largest importer of gas in the world. Germany imports its gas entirely from within Europe, whereas Italy gets a fairly big chunk of its gas from North Africa. And the emissions from the upstream sections of the supply chain, they are higher for the countries in North Africa than the countries in Europe. And that's one of the main reasons why Italian gas imports have higher emissions than the German. Now, if you compare the kilotons methane emitted with the emissions intensity, so the emissions intensity is your quantity of methane emitted divided by your total gas throughput. So it's an indication of how leaky your supply chain is. If you compare this graph with the previous graph, we can see that it's a more or less a completely different picture. The US domestic production and Russian domestic consumption supply chains, while they were the highest emitters in terms of their emission intensity, they're actually less than average and around medium. The reason why these two supply chains were so high in emissions is because the gas throughput for these two was by far the largest out of all the supply chains, and consequently that resulted in the high emissions despite having a less than average emissions intensity. Similar to the previous slide, when we compared the emissions intensity across the supply chains, again, there was a wide variation from 0.01% to slightly over 8%. And in general, it's the countries and supply chains that have a higher reliance on the tier 1 method, and therefore the IPCC emission factors that have higher emissions intensity, as emissions estimated using tier 2 and tier 3 methods tend to be lower than emissions you would estimate using the tier 1 method. As you can see on the graph, when we compare the emissions intensity with our benchmark for the risk assessment, we can see that there are a large number of supply chains that have emissions well above this benchmark, and that had a significant impact on our risk assessment, which I'll show you in a couple of slides later. So moving on to our uncertainty assessment, when we compared the emissions data that we collected and compared the different methodologies used by the different countries to estimate their emissions, we found that there was a very high dependence on the tier 1 method. And consequently, that means that a lot of countries don't have the actual emissions data, and they rely on de facto emission factors to estimate their emissions. And this also had a very big impact on our uncertainty assessments of the emissions data. When we carried out bootstrapping resampling on our emissions data set and omitted the tier 1 data, we found that there was significant reductions in emissions. So in the upstream emissions, there was a 3.8-fold reduction. And for the downstream stages, there was also a reduction, but less dramatic, around 47%. The reason why production and processing experienced such a large decrease in emissions is because the countries that we collected data for, there was a higher dependence on the tier 1 method in the emissions accounting for those countries, whereas in the transmission and storage and distribution stages, the countries we collected data for these stages, there was a heavier use of the tier 2 and tier 3 methods, and hence a less of a dependence on tier 1. So overall, this would suggest that the emissions estimates in the previous slides would be an overestimate. However, our risk assessment identified that there are a large number of countries that are at risk of high emissions, specifically at risk of having high emissions and not properly accounting for it. And when we take this into consideration with the results of our bootstrapping resampling, we are overall unable to determine whether or not our emissions estimates are an over or underestimate, partially because we couldn't fully determine how accurate and representative the tier 1 emission factors are for the countries that use them. However, our results do indicate that there is a high level of uncertainty within the emissions data. There's a large number of countries that don't have emissions data, and therefore, if methane abatement strategies are to be implemented and be effective, it's critical that this kind of data is collected, and so that measurements, methods and measurements can be taken to effectively reduce emissions and also track methane emissions, as it is a highly potent greenhouse gas. Can I just ask, how am I doing for time? Because I feel like I'm going very fast. I only have one slide left.
Okay.
Okay, in which case I'll move on to my final slide.
Yes, yes, for sure.
Yeah, so in conclusion, in total, we estimated that 26.4 megatons of methane were emitted by all of the 252 supply chains that we considered. And when we compared the different supply chains, there was a wide variation within the emission ranges from less than 0.1 kilotons to well over 1,000 kilotons. However, on average, 134 kilotons of methane was emitted, which indicates that there are supply chains that are significant outliers. When we converted the emissions into emissions intensity, again, there was a wide variation in the intensity from 0.01% to as high as over 8%. And again, there were countries and supply chains that were significant outliers, as the overall average of the supply chains was around 1.7%. When we conducted our uncertainty assessment of the underlying emissions data, we found that there was a high reliance on tier 1 method and IPCC de facto emission factors. And this had a significant impact on our uncertainty analysis. When we resampled our emissions data omitting the tier 1 data, we found that there was a dramatic reduction in emissions. There was a 3.8-fold reduction in the upstream emissions and a 47% reduction in downstream emissions, which would suggest that the 26.4 megatons is an overestimate. However, our risk assessment identified that there's a large number of countries that are at risk of high emissions. So overall, we weren't able to determine whether or not this 26.4 is an under or an overestimate. However, our uncertainty analysis did indicate that there's a very high level of uncertainty within the underlying emissions data, and this is emissions that are reported to the UNFCCC and are included in national greenhouse gas accounting. Therefore, if effective measures are to be taken to meet these climate targets, then it's critical that more methane data is collected and that more measurement campaigns are carried out to be able to accurately establish what the level of methane being emitted by different countries and different supply chains are, as it's very important that we tackle methane if we are to meet climate change targets. Thanks.
Thank you so much, Jasmin. I would say that we have to quantify, we have to quantify, we have to quantify. And so thank you for your effort of quantification on these aspects, which is so neglected, but so important. So we will go on with the last talk, which will be given by Emilie. Emilie, here you are, I guess. I can't see you, but I can see your slide, your presentation. Could you hear me, Emilie?
Yes, I can hear you.
Okay, and I see you, so it's good. Thank you so much, Emilie. The floor is yours.
Okay, thank you. Good morning. As said earlier, my name is Emilie, and I'm a PhD candidate in environmental science at the University of Lausanne in Switzerland, and also currently working as a research fellow at the University of Applied Science in Valais, Switzerland. So I'm very happy to be here to present you the work of my colleagues and I, where we explored how combined heat and power plants fueled with natural gas might represent a short-term solution to produce power in winter on the Swiss territory. And we look more precisely on the effect on the hourly carbon footprint of the electricity consumed in Switzerland. As most of the paper presentation, I will start by introducing you to the background behind the paper. Then I will present you our research questions, the method we used, and then the result and conclusions. as many countries around the world, Switzerland has committed to a transition to a low carbon energy system, and it has been done through its energy strategy 2050, which relies on 3 pillars, which are promotion of new renewable energy, as well as hydraulic power, but also saving energy and increase efficiency in building, mobility, and industry. And the last pillar is nuclear phase out. And the last pillar means that the country will have to replace around 35% of its electricity productions. So it's a huge challenge. And in the long run, it should be compensated by the deployment of renewable energies and the reduction in consumption. So the 2 other pillars of the energy strategy. But currently, imports from the European Union are used when indigenous production is unable to meet demand. So for the last years, the use of electricity flows from neighboring countries has been growing, especially in winter. So the Swiss Federal Electricity Commission has warned about this winter dependency and think that it's a threat to the security of supply, and has also warned that the majority of imports are of fossil origins. So they conclude that a substantial amount of this missing winter production should continue to be produced on the Swiss territory. So basically, Switzerland needs a temporary solution to produce electricity during winter on his territory. So my colleagues and I decided to look at if combined heat and power plants fueled with natural gas can be that a short-term solution, as it is a highly efficient and energy conversion process. So it leads us to our 2 research questions, which are, the first one is, what is the impact of the electricity inflows from neighboring countries on the hourly carbon footprint of the electricity consumed in Switzerland? So how does imports impact our electricity consumption? And second question, say how the replacement of part of those inflows from neighboring countries by combined heat and power plant fueled with natural gas impact the hourly carbon footprint of the electricity consumed in Switzerland. So is the situation better or worse if we substitute a part of those imports? So to answer those 2 research questions, we develop a 4-part method where we first assessed on an hourly basis, and that's very important to point that out, the greenhouse gas emission from electricity consumptions, and we measure the impact of imports. To do that, we use the consumption accounting principle, meaning that we took consideration production, importation, and also exportation. And we used the attributional life cycle analysis approach. We used data from the EcoInvent database to gather all the emission factor of different technology for different countries. And also we accessed the NSOA transparency platform for all the hourly data on generation, power generation, and physical exchanges between countries. So the scope of this part was that we took only into consideration physical exchanges with first ring countries, meaning direct neighbors, which are Germany, Austria, Italy, and France. Then we modeled hourly gas consumption in Switzerland, but for heating purposes only. To do that, we use a top-down econometric approach using the degree hours method according to a Swiss standard. And data were made available by the company who transport and deliver high-pressure natural gas to Western Switzerland. Based on that model on heating demand, we simulate hourly electricity production with natural gas CHP plants. So we use the top-down approach. And the rationale behind it was that heating demand had to be covered by the electric thermal output of the CHP plants. CHP plants were considered as linear, so a converter with fixed electrical efficiency. And the parametrization, we took them from the database EcoInvent also 3.7.1 for electricity produced by CHP in Switzerland. And finally, all those three steps allow us to assess the hourly GHG emission from the electricity consumption in Switzerland with the CHP solution. To do that last part, we use the conditional attribution, meaning that the electricity produced by CHP was at first intended to replace imports, but independently from the country of origin or from the technology. So the results shows that imports from Germany impact strongly the carbon footprint of the electricity consumed in Switzerland. So as we can see here in the chart presented, where here we have inside the greenhouse gas emission and outside electricity, we can see that imports from Germany, so in blue here, accounts for 90% of the electricity consumed in Switzerland, but it accounts for 74% of the carbon footprint of the electricity consumed in Switzerland. So that's huge. For only 90% of the electricity, it represents 74% of the carbon footprint. On the contrary, the domestic generation of Switzerland, so in light blue here, we can see that 67% of the electricity consumed in Switzerland is from the own domestic generation, and all those 67% account only for 13% of the carbon footprint. So basically, Switzerland has a very clean domestic power generation, and the impact from Germany is very strong on the carbon footprint. What is interesting to see is that this effect is kind of fading through time as the weight of Germany imports is getting lighter and lighter, going from 74% in 2016 to 65% in 2019. And this is mainly because the share of coal and lignite in the German generation mix is constantly decreasing. So here in the graph below, we can see that we have Switzerland inside and Germany outside. So Germany outside, we can see that in 2016, 40% of its power generation was from coal and lignite, and 29% from new renewable energy. And we can see that through time, this is changing, and the power from coal and lignite is getting smaller and smaller to reach 29% in 2019. And we can see that the share of new renewable energy is increasing to reach 42% in 2019. So also why Switzerland has so clean in terms of CO2 power generation is because it's mainly composed of hydropower and nuclear power. And it's quite stable through time, except that this nuclear power will have to be replaced in the medium term. So another important point that we wanted to point it out is that the emission factor, the hourly emission factor of the electricity consumed in Switzerland varies a lot. Especially, we can see huge difference between summer and winter. So that's a really important fact to take into account this time varying aspects, because when we consume 1 kilowatt hour of electricity in summer here, that was our always the down curve, we can have 100 times heavier footprint when we consume the same kilowatt hour in winter. So that's something which is very important when we thinking about electricity consumption. Finally, the next table will show you the emission factor of the electricity consumed in Switzerland. So here on the left, you have the actual emission factor for the year. And we can see that it's actually getting better. This is mainly due to the German mix getting cleaner, as I told you earlier. And next, we got the new emission factor after we run the analysis, the simulation with the combined heat and power plants fueled with natural gas. And we can see for the year 2016 and 2018, it will have been a benefit for Switzerland, but as the generation mix is getting cleaner, it will have increased a little bit the emission factor of the electricity consumed in Switzerland. Our simulation showed that CHP could produce nearly 10% of the electricity consumed of Switzerland. So it's here we can see that it's in green. It's around 10%, 11% in 2016 and 9% in 2019. And it will account for around 25% of the carbon footprint. And we can see that it lowers the impact of the German imports to 52%, around, and 39% for 2019.
You have 5 minutes. 5 minutes left. Okay.
Yeah. I've been super fast. I only have one slide left. So in conclusion, what we did is that we adopted an hourly approach to evaluate the carbon footprint of the electricity consumed in Switzerland for the year 2016 to 2019. And we were able to measure the impact of the electricity import from neighboring countries, also from Germany, France, Austria, and Italy. And we were able to simulate how the deployment of CHP fueled with natural gas would impact this carbon footprint. So the results are show that the Swiss dependency on electricity imports during winter has a non-negligible impact on the environment. It's heavily impacted by imports from Germany, but it's fading through time. Another important point is that the range between which the carbon footprint varies is huge. The difference between winter and summer is very important. And finally, that's the CHP solution examined in this study could represent a short-term solution to produce power in winter. But as we saw, the benefit is fading through time as the energy system is getting cleaner. So further research should be done in Switzerland to measure the effect of nuclear phase out. Because for the year that we covered, the nuclear power plants were still working on. The first nuclear power plant has been decommissioned end of December 2019. So it will be very interesting to analyze the years 2020. And also it will be very important to analyze the costs and the feasibility of the deployment of such a solution.
Thank you very much.
Thank you,
Emilie, for this talk focusing on a so nice country, your country, Switzerland, in the middle of the EU, but with several external links with the EU, at least regarding electricity. So we have time for a Q&A session, and maybe I would like to start with a question which was asked to Ahmed. If you look at the chat, Ahmed, you had a question from Hakim. Is Hakim here? I don't know. I don't think he is here. So, so the question asked by Hakim is about how you could force up the level of natural gas while the emission is more abated. So you have maybe to explain more about with the CCS. I leave you the floor to answer this question, Ahmed. Microphone, your microphone.
Yes,
Okay.
yeah, maybe I will be sharing my screen again just to show the. Okay, so here, what I mean, the key principle of our modeling is to investigate the possibilities of forcing more renewables in the global power generation system, and also more gas to coal switching. What is the potential, which regions, and where we can force this? What are the main results that we obtain? If we see the emissions here, we see that in 2050, compared to the reference case, the power-related emissions were estimated at 12 gigatons CO2 by 2050. By forcing renewables and forcing coal to gas switching and other options also, so we can reduce by third. If we don't apply the CCS, if we apply the CCS, we can reduce the emission by 50%. This is based on the existing and well-proven technologies, of course. Here, the decline of coal, if we count the emissions which result from coal, we see that the amount of reduction is huge from coal, because this coal is replaced by renewables and also by gas. For natural gas, when we don't consider the CCS, we see some increase of the emissions, because when we increase the power generation from natural gas, we increase the emissions. We are talking on the CO2 emissions from the combustion of gas in the power plants. So if we apply the CCS and we estimate and we assess that the potential of applying CCS is very, very important for gas, especially in North America, but also other countries in Europe, also in the northern sea. There are some potential in Germany and also in Poland to deploy CCS in the power plants, and this will reduce. We need to reduce the gas, the emissions from gas power plants, even when we force more natural gas. So this is the main results we obtained. Okay, thank you, Ahmed. But I continue to wonder if you have CCS and if it is not so costly and if it is feasible and so on, why you don't use CCS only or mainly for coal, and why do you have to switch from coal to natural gas? Because it will be more beneficial to use CCS for coal. I mean, if you have a CO2 tax, then your CCS cost will be better absorbed with coal and gas. So could you explain this to me? Yeah, there are two reasons for that. The first reason is that regulation in many countries are phasing out coal, are restricting coal, and there will be a significant coal decline in many countries, even in China. Even in China, they announced a gradual decrease of coal after 2035. So this is the first reason. And the second reason is because of the cost. When you deploy CCS on the gas-fired power plants, is 1/3 to half. It costs 1/3 to half the cost of deploying CCS on the coal-fired plants. Why? Because you need less infrastructure, less. I mean, the capacity, the amount of CO2 you need to capture from the coal is much more important than from gas. The carbon intensity of coal is almost 2 times the one of gas. So you need to increase the size of the facilities, of maybe the pipelines that you need to transport the CCS and the capture also. Even the efficiency of the capture is better from natural gas. And also you need to remove all the pollutants from the coal. The NOxes, the sulfur dioxide, sulfurs. Gas is free from these pollutants. So this is why, I mean, economically is better to deploy CCS on the gas-fired power plants. Okay, thank you. I did not know that. It's very important. Thank you very much. I have a question to Giacomo. Giacomo, you are here, I guess.
I am, at least in spirit.
Yes. Okay, but I am only interested with your spirit, so it's okay. My comment or my question is about regulatory capture. I mean, in your setting, you have a perfect regulator, I mean a benevolent regulator, but who has to cope with imperfect information. But because we don't have a world regulator, maybe we can also take into consideration that the regulator could be captured, saying that in fact I have imperfect information, but in fact he has the information, but he will say to his principal that the information he knows the information, but he will say no, it's imperfect, it's an error. So I think that you could add this to your model without any strong modification, just to take into consideration it's not only a matter of imperfect information, or it's also a matter of imperfect information about what the regulator is doing.
Yeah, I think maybe I was not clear in what I was saying. I got a solution for the social planner, and then I got a solution for the decentralized economy, and I get essentially three results. So the first result is that if you have a social planner who is a benevolent dictator, only interested in well-being of human beings and has perfect information, there is no flaring, there is no venting, there is a high level of expenditure in the maintenance of the gas equipment. If you have a decentralized economy, you have in equilibrium a positive level of flaring, a positive level of venting, and you have structural underinvestment in the maintenance of the gas equipment, because it is rational to have leakages, so to get rid of some of the gas that you don't want to process. And then what I tried to do was to design a tax system where you get, in a decentralized economy, you get the same type of result that you would get under a social planner. And what I could not do was to do a Pigouvian tax because of asymmetric information. So what I did is, let's try to make this gas profitable. And this is very controversial, right? This is something that you don't really, every time I talk with people, say, oh, let's give money to people who produce gas. It's total anathema. But the idea here is, let's give a little bit, let's tax you a little bit more if you get oil out of the ground, and let's use a little bit of those revenues to make the gas profitable for you, so that all the incentives goes for you to sell the gas. And at this point, you already have an advantage because you have no flaring and less venting. But what I tried to do also was to exploit also the interfuel elasticity of substitution in the power sector, so that I gave a rebate to the power plants who use natural gas. And instead, I didn't give that rebate to power plants who use coal. And this means that in equilibrium, the price of gas goes back to what it was before the policy. Only now the incentives are for upstream to don't get rid of the gas, and for the power sector to try to substitute coal with natural gas.
Okay.
But I recognize that this policy, I give this presentation to the Environmental Defense Fund a couple of weeks ago, and I thought they wanted to kill me. So, I mean, I recognize the...
I don't want to kill you.
Thanks. I recognize this is not necessarily the right thing to do. But what I would like to do, and this I think also goes well with what Jasmin said, we have very bad measure about methane emissions, and the more you go global, the worse they become. And there are countries we know nothing about, like Russia has, I saw some Bayesian estimation of Russians, it's total, we know nothing. And so the solution was to try to put the incentives of the producers in the same direction of the one of the regulators. So everybody goes in the same direction.
No, this is why it is interesting. Thanks to Giacomo. Jasmin, you made a quantification. Do you have any policy recommendations? Because Giacomo has, and also Emilie, and so what is your policy? What could be the policy recommendations, knowing your results?
Well, based on my results, I guess policy recommendations could be more around, for the countries where there is data, it's more towards managing and improving the quality of the data, because even within the different tiers, so even within a tier 3, there's a wide variation in what you actually have to do to qualify to be a tier 3 method. So a lot of it goes around trying to make sure that you update your emission factors every year, or just try to make sure that you are monitoring your emissions constantly. I think there should also be something around like knowledge sharing between different countries, because like as Giacomo said, and that's shown in my results, there's a lot of countries where they just don't know anything. And the IEA recently launched a report, I think it was earlier this year, that was a roadmap on how countries could start to tackle the issue of methane. And a lot of it goes around how they can go around measuring their emissions. I think for regulation, in terms of like policy, it's definitely going, there should definitely be an emphasis on trying to establish what the baseline is, or what your methane emissions are. And then once you've established that baseline, what can you do in terms of setting targets for reducing your emissions, as well as what methods and measures you could realistically implement to reduce your emissions.
Okay, thank you. And Emilie, electricity is not like oil and natural gas. It's very difficult to say where does it come from in Europe. So I would like to get from you more details about how do you consider the imports? I mean, and the contents of the imports. Because did you look at the contract? I mean, there is a contract between a supplier and a user, and the contract is between a German supplier or a French supplier, or did you take into account the imports at the border? Because sometimes, even if you import from Germany, it's electricity from elsewhere, from France, or so. I mean, it's so difficult in the EU to know the origin of the electricity. So, how did you cope with this difficulty?
So we took actually the actual physical cross-border flows. So we look at what goes in and out at the border. So
Okay.
And because it's information which is recorded and made available, publicly available on the transparency platform. So, and we know that we made the hypothesis to take only first-ring countries into account, but it's true that imports from Germany are not only imports from Germany, but also contain a little bit of Poland, of France, and so on. So it's a hypothesis that we took, and we have done another study, which I will present Friday on the Florence School of Regulation. We took this time into account the secondary country as well, to see if it changed the results much or not, and actually didn't change a lot. The results are basically robust.
Okay.
If we took only first-ring country and also second-ring countries.
Okay, good to know. Okay, thank you, Emilie. We have time. Maybe you want to ask to each other some questions. You would like. So
maybe
yes, Ahmed.
maybe if you allow me, just I want to ask one question to Giacomo regarding the methane emissions. It's a very hot topic for the gas industry, and I mean, Giacomo and even Jasmin showed the inaccuracy of data and the difficulties to measure data. Just I want to know in your approach, because the problem is not on reducing the venting or reducing the flaring. The problem is on reducing the emissions. How to reduce the emissions, and maybe in your model, you should include the objective to reduce emissions. Why I say this? Because maybe one way to reduce emissions is to flare more gas instead of venting it. Because if you flare the vented gas, you will reduce emission by 20%, because the CO2 equivalent of the vented gas is 20 to 30 times more than the vented gas. So maybe there is a need, at least for, I mean, at the beginning, for the beginning stage, to see how you can flare this vented gas if there is no possibility to value it, or if it's difficult to invest for this, flare it, and after that you can I mean, reduce the flaring. So this approach can be one way to do it as a short term.
I think we are going in a different direction, in the sense that the regulator is capable of seeing flaring, and so they want to ban flaring. You know, for example, the Canadian government has now very tight regulation on flaring. The US government is a little bit divided between different states. Norway is also reducing flaring quite a bit. So I understand your point of view. I'm on board. Let's flare everything instead of venting. I don't want to vent one single SCF, but it seems the regulator is going in a totally different direction.
Because if you keep learning 30 times more than, I mean, the equivalent than venting, it's
one option that I did not take into consideration is the possibility of making reinjections. Now, the point with the reinjection is that for me was very hard to deal mathematically, because you get the gas out and you put the gas back in, right?
Yeah.
But one of the things that this does is that it lowers the marginal extraction cost of oil. So everything else equal, it becomes cheaper to get oil out from the ground. So maybe you don't get the emissions from the combustion of natural gas or the venting of natural gas, but everything else equal, you get more oil at a cheaper price out from the ground, and this maybe has also some environmental impacts.
Jasmin,
within the oil and gas sector, flaring is actually considered like best practice, one of the best practices to avoid venting, which is kind of weird, but it's mostly related to the impact of methane. However, for the practices to reduce both venting and flaring is to essentially have, as Giacomo said, to like sell the gas. So either connected to a gas pipeline, or you can compress or liquefy your gas and then sell it. But yeah, it's kind of weird that flaring is actually considered a best practice alternative to venting.
But also I think there is a little bit of lying there, in the sense that, so for example, if you go in the basin between Texas and New Mexico, you know, the Permian, if you go in the Permian basin, it is clear that people are making sure that the gas equipment doesn't work very well, because they want a very big number of leakages, because they can't cope with all the gas that is in the pipeline. So what they say is that, oh yeah, we would like to flare as much as possible, but then, you know, when we have airplane monitoring, it is clear that the gas infrastructure is under-maintained on purpose, and that part of the thing is just let it go, because we cannot deal with all this gas.
Okay, other questions?
Yeah, actually, I have a question for Giacomo and for Emilie. So for Giacomo, did you find out any difference between like the larger oil and gas companies and the smaller gas companies in terms of who was venting more rather than flaring? Because from my communications with some of the bigger oil and gas companies, they do have more of an incentive to reduce venting from basically capturing the gas and selling it. So I was just wondering if you did find a difference between the two.
I think I found a difference, which was big companies often do not own a lot of shale. A lot of shale is owned by small operators, and people who are in shale tend to flare and vent more, because these are new producing regions that have worst connection. And instead, you know, if you're operating at standard big field in Western California, it's probably reasonably well connected. So I don't think it's really big versus small, but it's more than small are operating more
conventional versus unconventional type,
and that small are operating more unconventional, at least in North Dakota and Texas, New Mexico.
Okay, cool. For Emilie, I was just wondering, in your LCA, what impact assessment method did you use? And specifically for hydro, is methane emissions included from the reservoirs?
So we used attributional life cycle emission approach, and the EcoInvent database is taking it into account the whole chain from cradle to grave of each generation type. That is also why for Switzerland we had only nuclear power and hydropower, but it still emits greenhouse gas emissions. So it took into account all greenhouse gas emission, but converted it into CO2 equivalent according to global warming potential for 100 years, like IPCC.
25, or was it 34?
Okay, thank you. Unfortunately, we have to end this session. I would like to thank you, everyone. It was very important what you made, because it's so important to quantify and to quantify. So, and of course, with some policy recommendation from your quantifications or your modeling. So thank you to all, and see you somewhere. I don't know when, but congratulations for your work, for your research, and have a good future. Bye-bye.
Thank you. Bye.
Bye.